Okay, so good evening, everybody. Thanks for coming to our fifth lecture. So let me briefly remind ourselves of what we have covered in the last lecture. Okay. So, right. So in the last lecture, I went over the whole ADM quantization procedure, explained to you the concepts of constraint, what the constraints do, and we briefly talked about the quantization procedure. And then I suggested the exercise, which is about performing this quantization for FLRW or the ADM splitting. So I think this is a very, very nice exercise. I think if anybody wants to get a handle of the ADM formulation and also the Wheeler-DeWitt equation and so on, this is a very useful exercise to do. So I'll put this in red. Then we finally reached, well, gauge theory, and I start talking about the first order formalism of gravity, and then introduced these two concepts of a gauge connection and a tetrad. Right. So a tetrad is this soldering form, and what it does is it connects, it maps one. So you have a man. Okay, let me just see what else. Right. Yeah. On a manifold, you can have at each point you have a tangent space, and that tangent space is, so if your manifold is locally a Minkowski manifold, right? I mean, if it has topology R31, then locally it will have tangent spaces which are Minkowski spaces. So you can think of it as a fiber bundle, right? So a fiber at there's a base space which is your manifold, and at each point on that base space there is a fiber, and that fiber in this case is that tangent space which is the Minkowski space. And you can also attach another fiber there, which is the space of spinors. And so this soldering form is a map from the tangent space, the Minkowski tangent space, to the space of spinors. That's one way to think of it. And right. So then I start talking about what local gauge transformations, what gauge transformations are. Right. So gauge transformation measures how a field changes from point to point. So in the case of a scalar field, for instance, a complex scalar, a gauge transformation is just a multiplication by a complex number, a phase, right? If it's a constant, you have a global phase. If it's a variable, if it's a field, if theta is a field, then you get a local gauge transformation. And then I explained how if you construct the action for a complex scalar, and then you impose the requirement that so this is impose the requirement that this action should be invariant under these local gauge transformations, then that is equivalent to, that implies that requires one to introduce a new notion of a derivative, which is also a covariant derivative. So which is the partial derivative plus this quantity mu acting on phi. And then the action becomes, it's only the kinetic term in this case, so the kinetic term changes. and this is invariant under local phase changes. So local gauge transformation. So again, this is a exercise that you must do. And okay, then we come to the fact that gauge fields themselves are dynamical entities, as shown, for example, by the case of electromagnetic theory. So for electromagnetism, one writes an action which has this form, where F mu nu is this antisymmetric tensor, and this has exactly the same form as the antisymmetric tensor as a Riemann tensor. So we will see that the similarity becomes clear later on. So if you imagine that instead of A, you put the gamma symbol, right? Then this term d mu a nu, my antisymmetrized, looks just like the first term of the definition of the Riemann tensor, which is d mu gamma nu, and then antisymmetrized. But then the Riemann tensor has two other terms, which involve products of gamma tensors. In this case, we don't have those two terms. We don't have those extra terms because here we are talking about an abelian gauge theory. It's an abelian gauge theory because the gauge group, right? So these gauge transformations, they are elements of some group. In this case, they happen to be elements of U1, right? So I will explain what that means. And so you can, when you construct a non-abelian gauge theory, then what happens is that the curvature that you can define has two additional terms which involve products of A, which go like A square. So this non-abelian curvature looks structurally almost the same as the Riemann tensor. And then using this soldering form, we can give a one-to-one mapping between the curvature of a non-abelian gauge field and that of the Riemann tensor. So we'll see that also. Then I tried to motivate the reasons for these gauge transformations and the existence of these gauge fields, right? And it arises, for instance, and the way this behavior arises in the case of electromagnetism, right? And then, right, and then finally, I mentioned that. So an example is that if you take a charged particle in an electromagnetic field, and you transport that charged particle from one point to another point, then that charged particle picks up a phase which is given by the integral of the line integral of the vector field along the path taken by that particle. Okay. So now let's look at what happens with so let me define what is a gauge field properly. What is a gauge transformation? Gauge transformation. Okay, so the technical definition of a gauge transformation is that it is a map it is a map from your manifold, whatever your manifold happens to be, to the gauge group, to your gauge group G. Right. So at each point of the manifold, you assign an element of the gauge group. Okay. If you have a U1 field, for instance, you assign a complex phase at each point of the manifold. And one way to visualize the effect of a gauge transformation is to think of, consider this, that you have a, let's say that you have a spinner field that is defined on space-time, okay? Or you don't even need space-time, you can think of a lattice. And on this lattice, at each vertex, you have a spinner, and the spinner is in, let's say, the up state at each site. Or at each space-time point, okay? Now, imagine that you apply a gauge transformation to this. So one second, just do not. So what is the effect on this collection of arrows? Well, you can visualize that by, so first of all, what will be the gauge transformation on a spinner, right? So a spinner, right? If we talk about a spinner, for instance, it lives in a Hilbert space, right? And that Hilbert space is the space of a spin 1/2 particle, right? And this is two-dimensional. So we would write a state such as this as something, let's say 1, 0, and the down state as 0, 1, right? So our gauge group is determined by the structure of our matter fields. So these are our matter fields. And what are the symmetries of this matter field? The symmetries of this matter field are that you can apply any unitary operator, right? So any unitary operator, U, when it acts on one state, will give you another state, right? Another way to think, any unitary operator, you take a spin and transform it into a different spin, right? And let me just mention that one doesn't need to work with a quantum particle. One can equally well work with a classical field. Let's say we work with a classical vector field. So that means you have a scalar field phi. Only the thing is, it has more than one component. So phi I x, where I goes from 1 to however many components the field has. Maybe n is a better way. And then what is the group of symmetries of such a field, right? So the vector phi, right, phi 1, phi 2 till phi n. What would be the symmetries of this? Well, the symmetries of this would be SON, right, which would be the group of rotations in n dimensions. So here the group of rotations, so actually not, any unitary operator, so that would be SU2. SU2. So here the group of symmetries is SU2 for a spin 1/2 particle. And so you imagine that you have a gauge transformation. So you assign an element of, in this case, since I'm talking about spins, you will assign an element of SU2 at each point of the manifold, right? Then what does that do? If that element is the identity, let's say at this point here, G is equal to the identity, then the spin at that point is unchanged, right? But then you look at slightly different location, and here now G is not the identity, right? Then compared to the spin at this point, right, this spin is rotated. Now, the key statement here is compared to the spin at the other point. So then the question will become, how do we compare? So if you are in a curved manifold in general, right? This spin is at one point, this spin is at another point. So the question will become, well, how do you compare these spins? Because they live in tangent spaces which are not the same. And that is where the notion of parallel transport will come into play. So we'll come to that also. So you can imagine that this gauge transformation is a field, and as a field, what it does is it rotates all the spins by some amount in this internal space. Okay, and it can be any rotation, it doesn't matter what it is. And of course, we will require this field to have some sort of continuity or regularity properties, right? So this is the gauge transformation. Now, okay, so
why do you restrict to SU2 rather than U2?
Rather than U2. Why SU2? Special unitary, right? Well, because yeah, you're right. I mean, in general, it should be U2.
Okay.
In general, yeah, U2. But if you want to talk about something which is related to, let's say, space-time, then you will have SU2, because for spatial vectors, you will, or a spatial triad, you will map that to SU2 spinors. So, okay. Okay. So now we can write down something called the equation for parallel transport. But before coming to that, yeah, let me define now this curvature for a non-abelian gauge field. So what is a non-abelian gauge field? Right. So as I mentioned, a non-abelian gauge field is one which corresponds to a group which is non-abelian, right? So how would I write down? First of all, how would I write down the gauge connection? So again, referring back to what happens if you transport a charged particle in the background of a gauge field, right? So if you take a charged particle and you parallel transport it, so if you transport it from one point to another along some path from A to B, then it picks up a phase which is given by this minus integral from A to B, A dot dx sine. Okay, and now in the U1 case, this is simply an abelian phase, right? But if you have if your state corresponds to the state of a spin, right? So if psi is a spin 1/2 particle, for example, right? Then this is your group element. Then G is an element of SU2. Okay. And how do I write down an element of SU2? Well, SU2 has a set of generators. So SU2 has a certain Lie algebra, I will write it like this. This is the Lie algebra of SU2, right? And the generators of SU2 can be written in terms of the Pauli matrices. So I can write sigma X, sigma Y, sigma Z. These are the generators of SU2, right? And I can write down any element of SU2 by exponentiating these generators, right? So I can write exponent minus I n hat dot sigma. This will be an element of SU2. And this n is a unit vector, a three-dimensional unit vector. Let's say n1, n2, n3. You can call it nx, ny, and nz. Right. So this is the same. This is what you would do, for instance, for rotations, right? Or right. So for rotations, you would talk about SO3. Right. Now, what is the Lie algebra of SO3? The Lie algebra of SO3. Again, so we'll write in small letters, right? And it has three generators. Let's say JX, JY, and JZ. Right. So, for instance, if you look at what is JZ, JZ looks something like this: 0, 0, then something 0, 1, minus 1, 0, something like this, I believe. Then, right, and these generators, they satisfy. This is the commutation relationship, right? So this is the Lie algebra commutator. And then in addition to this, they also satisfy the Jacobi identity, which is true for any Lie algebra. That if you take this cyclic sum of permutations, you get 0. JK, okay. And so I hope that you are all familiar with this Lie groups and all. If you're not, then you please tell me. I'm assuming familiarity with that. So what we want is that when you do this transport from one point to another point, you want to be able to write down the transformation of this state as, being multiplied by some element of your group. Something which looks like this, some linear combination of the group generators, this guy, right? And we want to be able to write that linear combination as an integral. So then what should be the form of our gauge connection? Oops. So if we define our gauge connection in this way, that our gauge connection, the technical name that is given to it is a Lie algebra valued one form, right? So first of all, it's a one form simply because it has one covariant index, spacetime index. And it's Lie algebra valued because it takes values in the Lie algebra of your group, right? So you can imagine, so rather than writing it like this, I should write like this. This is your non-abelian gauge connection. So what this tau I, these are the generators of your Lie algebra. And these are matrices, right? So this is a matrix valued object now. This A mu is a matrix valued object, right? And if you want to calculate the effect of this parallel transport of a particle from one point to another point, and the effect of the gauge field on this particle, then what you would do is you would do this. I will explain all these terms, what this P and all means. Minus integral I A mu dotted with dx mu. Okay. Now this integral again is a line integral, but now it's not a line integral of, this is not a scalar quantity, this is a matrix. So basically at each point along this path, or at each point in your space-time in general, you are associating a matrix, right? And then you're taking this integral from A to B. And this integral has to be something which is known as a path ordered integral. So this has to be, I'll talk about what this path ordering means in a little bit. Okay.
Deepak, could you please explain again how is that dot product a matrix? The integrand?
Yeah, 1 second. 1 second, I'll do that in 1 second. So this is a matrix simply because, well, you see this is a matrix, right? This A mu with a tilde in the bottom. So if I look at, for instance, SU2, then what is the value of A mu at a given point? It is A mu x sigma x, A mu y sigma y, A mu z sigma z, right? It's a linear combination of your Pauli matrices. So this belongs to an element of the Lie algebra of SU2, right? So this is a matrix, right? And right, so this is a matrix. Now I dot it with dx mu. Dx mu is the tangent vector at each point along the path. So if you dot it with the tangent vector, you will get a matrix, right?
Yep, I see it. Thank you.
Right. Okay. All right. Now, okay. So, what is the meaning of this path ordered? This path ordering exponential is defined in the following way. It is written, so if you have an integral of this form in general, when you have some integral in the exponential of some function, lambda, d lambda, along some path, okay, it doesn't matter what the path is, and you expand this, what you get is, well, you get the identity, then the next term will be just this integral from A to B, right? Then you might think, well, the second term will be this, f lambda prime, d lambda prime, right? Naively, this is what one would expect the second term to be in this expansion, right? So it looks like a Dyson series plus order lambda cubed and higher. And so if this is a path ordered integral, then this term would instead be written in the form So yeah, and there'd be factor 1 by 2 factorial. It would be written like this. Let's say you go from A to A prime and A prime to B. What that means is that I have this path. The beginning and end points are A and B. And then I take a point here in between, I call that A prime. Okay. And then I integrate over this d lambda from A to A prime and over d lambda prime from A prime to beta. And I multiply these products in that certain order. So such that on the left side I have, let's say, lambda prime, on the right I have lambda, and this is lambda prime, d lambda, d lambda prime. So this is just like a time ordered exponential, right? So remember that when you, in quantum field theory, when you have a time ordering operator, time ordering of operators in QFT, right? So let me do that on the next page. When you write down the unitary evolution operator, right? The unitary evolution operator in quantum field theory is written as this exponential of the Hamiltonian, right? From t, so let me call this tau d tau from t to t prime, right? But this exponential has to be time ordered. So again, when you expand it out, you want when you apply this time ordering condition, the time ordering condition is equivalent to this path ordering of this exponential. Okay, so in this case, you can just think of the parameter along the path, whatever the parameter is, it doesn't matter, right? It's a spatial path, but that along the path, there is just a single parameter. You can think of that parameter as your quote unquote time. And then you are time ordering your operator along that in terms of that parameter. So that's how you define this exponential. Okay. Anyways, so that is an important point, but I mean, we can forget about that for the time being. So this is an element of the gauge group, as I explained, because this is a linear combination of Lie algebra generators. And so when I integrate this, I get an element of the Lie algebra only, right? And that is how I relate these spinors or whatever my matter fields are, whether they are vector, this thing, n component scalar fields or spinors or anything else. Okay. So now I have this picture of matter, right? Which consists of something which lives in representations of some gauge group, right? So as an example, you have different kinds of representations of gauge groups, right? You have the fundamental representation, the adjoint representation, and so on. So we can think of these spinors. These spinors belong to the fundamental representation of SU2, right? In the fundamental representation of SU2. And then you have your gauge field. So the gauge field is what relates the matter fields at different points, right? So the gauge fields are elements of your Lie group. Right? So elements of SU2 in this case. Okay. And what is this connection then? This connection is like a tangent vector, but it's a tangent vector in this group theoretical manifold. So you have some sort of a group manifold. On that group manifold, you have a tangent vector. One way to think about this is that, again, in terms of this picture of fiber bundles, you think of this is your manifold, this is your base space, and this is your fiber. So your fiber, I will call it gamma. Actually, what is the technical thing? Let me just call it some vector space V. So my fiber bundle is my base manifold with this fiber attached at each point. And this fiber is it could be SU2, it could be whichever field you want. Okay, so you imagine that you have a fiber at each point. And then what is the meaning of a connection? A connection is that, well, so for the case of U1, for example, for V is equal to U1, right? For an abelian gauge field. What is a gauge field in this case? Well, a mu, right, assigns at each point of the manifold, it assigns an element of U1, right? So that means that each point of my manifold, this is my manifold, these are my fibers, at each point on my manifold, on the associated fibers, I have some point. I have picked a particular point. And so you can think of, in the terminology, this is called taking the section of a fiber bundle. You can think of this as a section of the fiber bundle gamma. Okay, so this is what your gauge fields are. Okay, now okay now there is another reason. So another very important reason why we need these sort of gauge fields, and we need them in the gravitational case. Okay, so these are some properties of gauge field. So now the question is, why do we need these gauge fields or connections?
Deepak, I had a question. If you
right? I mean, we are perfectly fine. We're talking about matter and curvature of matter and curvature induced by matter and so on. What is the need for these gauge fields? Well, because the regular or because the Christoffel symbols, yeah, Mustafa, one second. Because the Christoffel symbols don't know how to talk to fermions. Yes, Mustafa, please.
Yep, I understand you saying. Could you scroll up just a tad?
Mm-hmm.
Yep. So I understand the case in which you said that for the scalar field, the gauge field will be some element of U1. I don't understand what you mean by this section of a fiber. I don't understand it in that terminology.
So you just, I mean, okay, let me draw a simpler picture. Let's say my base manifold is the real line. Okay, so I'm in one dimension, and then on this one dimensional, at each point I have a fiber, right? And my fiber is a copy of my gauge group. Okay, and then I am taking an element of the gauge group, that is a point on this fiber, right? Something like this, let's say. So this is a section, right? And this is what I would call a gauge field, or one configuration of a gauge field.
So my question is there anything
Right.
special about the elements of the gauge field that you're picking here?
No, there's nothing special.
Okay.
There's nothing special. These are, I mean, you could just have identity everywhere, or you could have something which is, I mean, in what sense do you mean special?
You said that, I mean, for example, if you consider the 3+1 decomposition, then a hypersurface is a three-dimensional space which has the same value for t, the parameter t. I was wondering if there is something similar happening here, and you're saying there isn't.
So okay. So in the case of general relativity, what will happen is that our gauge group will be so I think you are confusing this. The t is the time, right? T is the constant time surface, sigma t. So I think you're confusing that with this vibration or fiber bundle picture. So if you want to talk about the fiber bundle picture applied to space-time, then for instance, your manifold would be your entire space-time manifold. Okay, let's say it's R31 or something with the topology of R31. Right? Then at each point on this manifold, again, I have a fiber bundle. I have a fiber at each point, and I can assign some gauge group. So what would be the gauge group in this case would be SL2C. So at each point, I would assign a element of SL2C. And this is at each point in my four-dimensional manifold. Okay. S2C gauge connection. I have nothing to this here. Weird. Yeah, hi. I got disconnected. So okay. Is the screen visible now? Hello? Can you
Yes,
guys hear me?
yes, we can hear you. I can hear you, and the screen is visible also.
Okay, cool. All right. So in this case, we would have an SL2C connection. Then when we perform this this splitting, this foliation, after the 3+1 splitting, what will happen is now our manifolds are sigma t's, right? It's something with the topology of R3. Now our fibers at each point, our gauge group will become SU2. And again, we will take some element of SU2 at each point, and we will write this as A, something like this, I. Now, A is the spatial index, and I is the Lie algebra index of SU2. So, anyways, we'll come to this a little bit later, okay? For now, let me continue explaining what is the motivation for having gauge fields, right? So the motivation is that, well, Christoffel symbol doesn't know how to talk to fermions. So because we already said that if you have fermions, then you need to introduce, or complex scalar fields, you need to introduce this covariant derivative. So so let me show you what happens to the action, the Dirac action, as an example. So the Dirac action can be written as something like this: d4x, then the Dirac conjugate psi bar, then I h bar c. We can not worry too much about these factors of c and h bar, but I'm putting them there anyway. So this is what the action for a Dirac field looks like, right? Where psi bar is equal to psi conjugate gamma 0. Gamma is the Dirac matrices, right? But now again, here what you have is the usual covariant, flat space derivative del mu. Okay. So now I can ask what happens under the influence of a constant phase e to the power of, let's say, some I g lambda x. So here g is some coupling constant. Okay, so g is just some constant. Lambda is some Lie algebra element, but it's the same for every point in space time. So under this change, what will happen? Well, you can see that psi bar will go to e to the power minus g lambda psi, right? And the action will be invariant, right? S Dirac is invariant. And again, for the same reason that the complex scalar action is, so if you do this, if lambda is not constant, then what happens is you have this derivative term, right? D mu. So you have d mu e to the I g lambda psi, right? And you will get e to the I g lambda times d mu plus I g d mu lambda. So this object, right, is what we write as our covariant derivative del mu, right? And we identify this a mu as d mu lambda. So it's exactly the same thing that happens in the scalar field, right? So if I want to write down the Dirac field in which is a sum which is invariant under these gauge transformations, I have to write down the action using this covariant derivative operator del mu psi. Okay. And again, it is telling us how the phase of the wave function is changing at each point. Okay, so okay, let's see. Okay, now let me come to the notion of the concept of curvature of the gauge field. So what do we mean by the curvature? So as I said earlier, for a abelian gauge field, this is the curvature, right? And it's an antisymmetric object, right? It's a two-form. Now, what is the definition for a non-abelian gauge field? So how do I write down my non-abelian gauge field? I write it as this, right? So how do I define the curvature here? The curvature should be f mu nu, right? I will get two indices mu nu from this mu index, and then I'll put a tilde here. You will see why. So let's say I write down this dA mu sigma I minus d mu. Okay, so okay. Now I can also write this as f mu nu I. I can put an index I on top of the f times tau I, right? So then I can write this as a nu I minus d mu I times I, like this. So this is the term I would write down, if I wanted to write down this gauge field. But the problem is that here I'm using my ordinary derivatives, right? But when you have a gauge field, then we must use the covariant derivative, the gauge covariant derivative, which we have introduced earlier. Which is this curly d mu, right? Now, so how should we define the gauge curvature using this covariant derivative? So working in analogy, with Riemannian geometry, right? We are calling this f mu nu, we are calling it a curvature, right? So, well, in Riemannian geometry, I would define this Riemann tensor in terms of its action on some object omega, which in this case is a one form. I can equally well write it as the action on some vector field just by raising and lowering this beta index. It's not going to make any difference, right? So this is the definition of the Riemann tensor, right? it is written as the commutator of this of the covariant derivative. So by analogy with this, the way I should define my my curvature tensor should be, it should be something that is related to this commutator of my covariant derivative. Okay. Now what is this commutator going to look like? Let's see. So if you were to write down the commutator of the partial derivatives, remember, this would be 0, right? Because ordinary partial derivatives commute. But what happens when we take our covariant derivative? So let's look at this guy, d mu. So again, expanding this out, and what is the definition for this? What is the definition for this covariant derivative? Let me just make sure I'm using the right. Did I mention it anywhere? Right. So this covariant derivative, and I think I mentioned it in the beginning also. Right, when I talked about the complex scalar field in one of the previous classes, that's when I mentioned it. So this covariant derivative, let me write it like this: a mu, and the second one is ig, a mu. Okay. Now this becomes d mu plus ig, a mu d mu, a mu d mu a mu minus g square a mu a mu. Okay, so this is our first term. The second term will be the same thing, only with the indices, order of the indices switched, plus ig, a nu d nu, d nu a mu minus g square a nu a mu. Okay. Now when I subtract these two, what do I get? When I subtract these two, I get this commutator. The ordinary partial derivative, these terms will cancel out, and I will be left with, and then these terms will also cancel out, a square term, right? For the time being, working with an abelian gauge field. And right, and then I have this term, but then if I ask what happens, right, this derivative has to act on some field, right? So if I ask that, if I say that it's acting on some field, then, you know, if you work out all the derivatives properly, the action of everything nicely, what you will get is the following, that this will be equal to minus d nu a mu. So let me work that out. Okay, better to be safe than sorry. So let me ask, what is the action of this on some field f? So I'm left with this term, remember, right? So I'll just use this term and see what happens. A mu d nu plus d nu a mu f. So ig A mu d nu f. Now the second term has two parts. One is d nu A mu f, and the other part is A mu d nu f. Okay? Ig multiplied by everything. Is this right? I think it's right. Then similarly, if I look at the anti-symmetrized version, again it will have the same behavior, and I'll get A nu d nu f plus d d nu A nu f plus anyways, I'm there is some I'm making some mistake somewhere. When you cancel out all the relevant terms, what you will be left with is this, that this is equal to d mu A nu minus d nu A nu, just acting on f mu nu times f. So this f mu nu is the curvature associated with our gauge field, and it is the curvature in exactly the same sense that the Riemann tensor is a curvature. This Riemann tensor is a curvature, right? And in what sense, what is the geometric notion behind this curvature? It is the following, that you start at some base point, you have some vector, in this case, or one form, and then you can move along two different paths. Let's say lambda and whatever, let's say 1 and 2. And so I parallel transport gamma, this omega mu along this path, and then I parallel transport it along this path, right? And the other option is that I parallel transport it along the second path first and then along the first path. So when I end up at the final point here, what happens? I end up with two different versions of gamma. One I obtain by transporting along the first path. Let me call it gamma mu nu 1 and another gamma mu 2. And these two are not identical, right? So there is a change, there is a deficit, right? This is exactly what this deficit is. Deficit angle is. So this deficit angle is measured by taking my R mu nu alpha beta and contracting it with the vector field along the first path and the vector field along the second path. So I can call this, let's say, this direction as V alpha, let's say, or V alpha, and I can call this, okay, U alpha, V alpha. So I'll put delta here. So this becomes something like this: delta V alpha, delta U beta minus delta V beta, delta U alpha, something like that. Sorry. This whole thing, so acting on this omega, and this is related to our alpha beta mu omega, something like that. Okay, I mean, indices we can all move up and down, it doesn't matter. So let's just write it like this. So it's basically related to how these vector fields, which along with which you are transporting your vector or your tensor, how these vector fields, they fail to commute. Okay. And now you can think of this, if you think of this in the language of fiber bundles, it becomes simpler to understand, and also to translate the notion of curvature directly to that of gauge fields. So here now, your fiber bundle, your base manifold is whatever your spatial manifold is, or your space-time manifold, let's say M, right? And what is your fiber? Your fiber at each point, is simply the tangent space at of that manifold. So TPM, which in the case of, let's say you're working in some space-time with signature PQ, would just be the corresponding Minkowski space with signature PQ, right? So if you're working in space-time, your tangent space would be R31. Let me just keep it simple at R31. And then I have, these are my 4 space-time points. And then I have some tensor which is defined at this point. Okay. And now this or some tangent vector. And where does this tangent vector live? It lives in this fiber bundle. So it lives in this fiber. So my omega is defined over here, omega mu. And then as I go from here to here on the base manifold along these 2 different paths, what happens? Okay, sorry about that. Right? Omega changes as I move along these paths. Right? So here omega becomes something else, here it becomes something else, here it becomes something else. So as I go along this path in the base manifold, the corresponding object in my fiber bundle, it is so transported along these 2 paths. So 1, 2, and 2, 1. And when I reach over here, this object, again, I have 2 copies, let's say omega 1 mu and omega 2 mu, right? And there is some deficit angle, right? In general, I'll call it a deficit angle. It won't necessarily be an angle because because I don't need to consider only one forms or vectors. I can consider arbitrary tensors, right? So if I have an arbitrary tensor, of type, let's say KL, then this can be written as living in the tangent space, in the tensor product of the tangent spaces and the tensor product of the cotangent spaces. Right, so this would be L and this would be K. So your fiber bundle would then become, your fibers would become this tensor product of the tangent spaces.
Why the tangent space is 3,1 rather than M itself?
No, because you are, okay, so, well, I mean, if you are in a, as an example, if you are on S2,
Mhm.
what is the tangent space at a given point?
It's just a tangent plane.
Tangent plane, right? And what is that tangent plane?
It's
It's
R2.
R2, right?
Yeah.
Right?
I see.
Okay.
So what is M here? The
So
original.
M is our space-time manifold.
Oh, so you are the tangent plane is a locally flat space.
Right. I mean, that is what a tangent space
I
is,
see.
right?
Okay, I got it.
So it's only thing is that now we are working with this language of fiber bundles. So in differential, so which is just a generalization of this tangent space picture. But now instead of tangent spaces, you have an arbitrary space that you can attach at each point. So here I have this tangent space, but instead of a tangent space, I can attach a Lie group also. So if I attach a Lie group at each point, then my fiber bundle, it looks the same. I mean, it looks like this. It looks like my base manifold. In this case, let's say R3, and my fiber is SU2, right? Or in this case, my base manifold is R31, and my fiber is SL2C, right? It can be anything. You can construct fiber bundles for anything, okay? You can take a circle as your base manifold. At each point on the circle, you can assign a fiber. Your fiber can be another circle, let's say S1. So at each point on the circle, you assign a circle. This gives you something which is called a hop fibration, right? Or it can just, so in this case, what is S1? S1 also corresponds to the set of phases, right? Complex phases, e to the I theta. So if you have, or if you have some real line, on this real line, you have some object that is living such that it has a phase at each point. Then at each point, you would have a fiber that is S1. Right? So the phase at each point would be some element of a point on this S1, right? So this gives you a geometric picture of these gauge fields.
Deepak, in the case of the complex scalar field that we spoke of earlier,
Yeah.
it would be your base manifold is R, and then the fiber bundle would be U1. Is that correct?
Sure. Yeah, the base manifold would be the space-time on which your field is living. So it would be R, you know, I mean, if your field is defined in 3+1 dimensions, it would be R31. Not, why did you say R?
I was just thinking of the simplest case possible.
Okay, fine. Sure.
Yeah.
Sure. Okay. So the point is that if you think in terms of this language of fiber bundles, and you translate your Riemannian geometric notions into this fiber bundle language, then these constructions, this construction of a curvature tensor, you immediately see that this is not something which is unique to these tangent vectors. You can define this curvature tensor for any fiber bundle, right? And how do you define this curvature tensor? By defining a connection. Okay. So, so in our case, our connection, so it happens to be this. So if it is U1, our connection is an abelian connection, and our curvature, corresponding curvature, is this 2 form. Okay. Now let's ask, what is the how do we write down the curvature tensor for a non-abelian field? Okay. So first, let me write down the covariant derivative for a non-abelian field. So let's say I have a spinorial matter, right? And this spinorial matter, I will say, has some index I. Or let me instead work with a scalar field which lives in the fundamental representation of SON. So I would write down my ordinary derivative, then I would have some G, which is a coupling constant. So if G is 0, then my gauge field doesn't couple to my matter at all, right? So that's why I introduced this G. And then what would be this this I? So I would write it like this. This acting on right. So instead of putting an index I, I'll just write a vectorial index and write it like this. So if you want to write it in terms of the components, so instead of I will use something like this. Let's say phi alpha. Alpha goes from 1 to n. And then what is this A mu? If A mu is some linear combination of my Lie algebra generator sigma I, or sorry, tau I. But you have to remember that each tau I is a matrix, right? It's the Lie algebra generator. And what will be the dimensions of this matrix? So since I'm in the fundamental representation, dimension of tau I will be n, right? So tau I is a n by n matrix. Okay, so for example, if I'm talking about SU2, my tau i's are just my Pauli matrices. They're 2 by 2 matrices. So then what is my connection? This connection is actually a matrix, right? So I should put 2 matrix indices on here. A mu I, tau I, alpha beta. Okay. And now if I write down this whole derivative in this matrix notation. Okay, so now I have d mu phi alpha. This is my space-time index. This is my quote unquote internal index, right? The degrees of freedom of the scalar field at each point. Okay, plus Ig, A mu I, tau I, alpha beta, right? And now this matrix has to be multiplied by phi beta, like this. So this would be how I define my this would be how I define my covariant derivative with all the indices explicitly shown. Now, is this okay so far? And I think that, you know, we are reaching the 1.5 hour point, so I'll not continue for too much longer. Let me define the curvature and then I will stop, okay? So now we want to ask what is the commutator of these covariant derivatives. So now I want to take two of these derivatives, d mu, in succession like this. All right. Now what will happen is that, see, if you apply two of these operators, so it's like taking the square of this expression, sort of, right? You will get two partial derivatives, right? But that term will cancel when we anti-symmetrize over mu nu. Then you will get partial derivative of the connection field, right? And then you will get the connection field times the partial derivative, though that term will also cancel out when we anti-symmetrize. But now you will get, you remember that in the abelian case, we got this a mu. And this cancelled out because a mu is just a number. But here, what will happen? We will get products of matrices, right? And those products will not commute. So we will get a term which looks like A wedge A or A commutator A. So when you work it out, I'll just write down the expression F mu nu, and I'll write down the like this, okay? So your final, this thing will look like this, okay? A mu nu alpha beta this is what your non-abelian field tensor will look like, curvature tensor will look like. And what is A mu alpha beta? A mu alpha beta is A mu I, sigma I, and sigma I is a matrix. Okay? So it's this guy. And what is the commutator, this A nu alpha beta? Well, this is just the commutator of two matrices. So one matrix is A mu, let's say alpha gamma. The other one we'll write as gamma beta, right? So we are just taking the product of these two indices. Again, my internet is being slow. Okay, sorry about that. Again, my internet disconnected. And am I visible? Okay, so now you can see what this commutator is. This commutator is just the commutator of these matrices. So this is expressed as the curvature of your gauge field, and it is defined entirely in analogy with the Riemannian curvature tensor. But there is a difference. The difference is that your Riemannian curvature tensor has four spacetime indices: R, mu, nu, let's say gamma, delta. These are all spacetime indices. but this non-abelian curvature has two space-time indices, and then these two are matrix indices. Right? So what is this F mu nu? This is a matrix valued. This is a Lie algebra valued. This is the technical term that you will encounter very often. This is a Lie algebra valued two form. Right? So it's a two form because, well, it's antisymmetric in mu nu, and it's Lie algebra valued because it's a matrix. Right? Each term is a matrix. So here you have a matrix, here you have a matrix, here you have a product commutator of matrices, that's also a matrix. So you have heard of Yang-Mills theory. In Yang-Mills theory, this is exactly the curvature tensor that you use. The gauge, the connection field, the gauge field that you use is depends on the gauge group. You can have Yang-Mills for SU2, you can have Yang-Mills for SU3, or any Lie group. What we will be doing is we will be looking at the gauge group SL2C. And then we will define the curvature tensor, the field strength tensor for SL2C. Then we will show that that curvature tensor can be mapped. There is a one-to-one mapping between the curvature tensor of the SL2C connection and the ordinary spacetime, the Riemannian curvature. But now we have the added benefit that we can write down a coupling to fermions, because we are working with an SL2C connection. So you can couple directly to SL2C spinors. Right? Dirac spinors. So I'll leave it here for today. I think this is enough material, right? And of course there are probably many gaps in my explanation. If there are any experts watching this, they are probably like experiencing various levels of horror at my exposition. But my goal is to like convey the ideas to ordinary mortals, or mortals like me, like I'm a mortal. And I think a mortal is somebody who can solve a quadratic equation. So, you know. And I believe that, you know, physics is not something that is the sole, what do you call it, private recluse, is that the right term, of only the mathematically gifted, right? If you look at high energy these days, it might seem like, well, unless you can understand at a minimum something like algebraic geometry and varieties and all kinds of other complicated mathematical structures, that you should not be in high energy physics at all. And I completely disagree with that perspective. Because ultimately physics is nature. I mean, this is just my personal philosophy, right? Nature is simple. Right? Nature is elegant. Nature is simple. Nature is not wasteful. And there is no reason that suddenly we, after hundreds and thousands of years of having experienced this fact that nature is simple and frugal, that suddenly, for some reason, we will now encounter that, oh no, nature was horrendously complicated to begin with, and you know, can only be comprehended by superhuman intellects. You know, and I completely disagree with that perspective, because it also creates sort of a caste system. It creates an inequality, an intellectual caste system, because it says that only those in this highest, you know, merit list are eligible to explore the mysteries of nature. Anyway, that's all my personal rant in philosophy, so you don't have to listen to that part. Okay, so I would strongly recommend that for those of you who have not seen these notions before, to look at Nakahara. So Mikio Nakahara has this book, Geometry, Topology, and Physics. It's a beautiful book. It's one of the most beautiful books I've encountered. Then there is another book by Baez and Munen. I've mentioned these books in Zule, by the way, in the literature section. So, okay, any questions?
I have one question.
Yeah.
So the Riemann curvature is one of the curvature of a non-abelian group, right?
So no, because there the thing is that the Christoffel symbols do not are not is not the connection of any group.
But when you write the Riemann curvature in terms of Levi-Civita connection, then it looks like to have a gamma terms, which is
right, Levi-Civita. So I think that's the same as this tetrad formalism. I think so. I'll have to go back and.
So it's not from non-abelian feature.
Let me just really quickly remind myself what the Levi-Civita connection is.
Mm-hmm.
Okay, internet is not working. So yeah, I mean, if there are gamma matrices, then yeah, it is a non-abelian.
Mm-hmm.
It will be non-abelian.
So what is the corresponding Lie group?
Well, so if you have gamma matrices, then I think you're working with SL2C, right? So it's the same kind of curvature tensor, or SO31, right?
Mm-hmm. Mm-hmm.
The Lorentz group.
Mm-hmm. And also, well, in case of a space-time curvature, so can we consider some time model which is abelian, not non-abelian one?
Oh, yeah, no, that's a really nice thought. Yeah, I'll have to think about that, because again, I mean, in a sense, curvature measures the non-commutativity of vector field, right? So if you have that non-commutativity, you have this non-abelian character. So if you have curvature is a measure of this often sort of, you know, non-abelian behavior of geometry or of things living on that geometry. I think so. No, maybe not. No, not necessarily. No, because you have non-abelian, you have the abelian curvature.
Yeah, but
yeah, I mean,
it's almost like just a kinetic term, right? Abelian curvature is almost like just a kinetic term.
Yeah, you can call it that, because especially because when you look at, for instance, when you look at this action term, right? This action for a abelian or a non-abelian field, right? So the time derivatives, they come, the derivative terms come from the abelian. So if you have an abelian connection, then you don't have any a square terms. You only have derivatives of a. So it looks like all kinetic terms.
Yeah,
if you want to think of it, like that.
I just realized that in case of space-time curvature, in Einstein-Hilbert action, there is no R square term, right?
No, but you can add an R square term, right?
Yeah, and this F mu looks like R squared. And
it does. It absolutely does. Yeah.
So why is there a difference? In case of a gauge theory, we have a F squared.
Right.
That's
so we can add. So we will see that our Einstein-Hilbert term contains one copy of F and one or more copies of the tetrad field. Okay, so it looks like E wedge F. Wedge is the antisymmetric product. Now you can always add, by the gauge invariance principle, you can always add any terms to the action, right, which are invariant under this symmetry. So you can add F square terms to that. You can add a Chern-Simons term. You can add a something called Neon term, Pontryagin term, Euler term. All of those you can add. Holtz term. And F square term also, right? So yeah, that corresponds to adding an R square term to the gravitational action. Then that becomes a higher derivative theory, right? If I'm not mistaken, R square terms are referred to as higher derivative theory. Right. Then there is another aspect, is that when you write gravity as a gauge theory, then the question becomes what happens to diffeomorphisms, because your what is the relation between gauge transformations and diffeomorphisms? And so it turns out that, well, diffeomorphisms can be written as gauge transformations. So there is a one-to-one correspondence. So you don't lose any information. So that I will talk about next time. One of the things I also did not properly cover in this session is the parallel transport, where this equation comes from. So I'll probably maybe give that as an exercise or something like that. Okay. And again, please, whether privately or in public, please don't hesitate to provide your critiques or corrections of anything that I'm saying. Okay.
Deepak,
yeah, Deepak, yeah.
So can you tell me again from the previous your first lecture that you have drawn some OH separate angles and
deficit angles and all that. Yeah, deficit angles and so on.
Deficit angle. I want.
Right. Sure. This, right? Dev Malle?
Yes.
This is what you're talking about. Right? So it's best illustrated with a real world example. Sheet of paper. Okay.
Yes.
taken a piece and I've
Okay.
removed it.
Okay.
Now you take these two edges and you glue them together.
Okay.
What do you get? You get something that people sell peanuts in, right?
Yes.
Which is a, and here there's a conical singularity at this point, right?
Yes. Huh.
Here there's a conical singularity,
Yes. Yes. Yes.
right?
Huh.
So if I take a vector now and I parallel transport it along a closed loop around this point,
Yes.
when it comes back, I will see that it disagrees with itself by an angle,
Yes.
and that angle corresponds to, depends on how much this, what is the deficit angle of this, which will be precisely equal to this angle, whatever angle I took out.
Okay.
So if I don't remove this and I take, if I take a closed loop, here
Yes.
anywhere, and I
Yes.
take a tangent vector and parallel transport it around that closed loop,
Yes.
when it comes back to itself, when you come back to the same point, the tangent vector will agree with itself.
Yes. Yes. Because it is flat.
Right. But here now, after removing something which has that angle,
Yeah.
and I do the same thing, the tangent vector will come back, and now this tangent vector is living in the tangent plane is SO2, right? It's a two-dimensional plane.
Yeah.
So the only rotations are parameterized by one number, right?
Yes.
So it will differ from itself by an angle which is precisely equal to this deficit.
Okay.
But the same way, what I can do is, so this corresponds to creating positive curvature. The same way I can cut this,
Yes.
I can cut a section,
Yes.
then I can insert a extra section in there,
Okay.
like this,
Okay.
right?
Okay.
Now it becomes a little bit harder to see,
Yes.
but this becomes negative curvature.
Okay.
Now there will be another deficit angle, but it will have an opposite sign.
Okay. Okay.
So this is in 2 dimensions. This is intrinsic curvature in 2 dimensions.
Okay.
Now you can imagine doing exactly the same thing in higher dimensions.
Yeah. Yeah.
You take a 3-dimensional ball, right? And you cut out a solid angle,
Yeah.
right?
Yeah.
And then what is left inside, you glue all of that back together.
Mm-hmm.
So again, you will have this conical singularity, and there will be a line or a surface defect.
Okay. Okay. Usually, when the thing is, I have read some paper from 8 of 10 Jacques in 1984 in 2 plus 1 dimensional gravity. They have
Yeah.
talked about the deficit angle and
That's
the
right.
closed time like path kind of things.
Right.
And from that, I am thinking that is it the same problem exists in the higher dimension, that is from the delta function singularity, the presence of the particle.
Well, no, I mean, so this is there's something peculiar happens in 2 dimensions, in 2 spatial dimensions. In 2 spatial dimensions, you can, if you look at, are you talking about gravity in 2 plus 1 dimensions?
Sorry, can you? The audio is not well. Can you tell
Are
me
you
again?
talking about gravity in 2 plus 1 dimensions?
Yes, gravity 2 plus 1 dimension.
Right.
The
So
paper
in 2 plus 1 dimensions, in the what happens is that gravity becomes a topological theory. It doesn't have
Yes,
any
yes.
local degrees of freedom.
Yes, yes.
And so, but what you can have is you can have defects.
Yes, yes.
You can have point-like defects. Those defects behave like matter degrees of freedom.
Okay, okay.
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 So those introduce, if you have these point-like defects, those introduce, I guess, some delta functions of curvature at that point.
Okay.
But only at the point where the defect is, not anywhere else.
Yes, yes. Definitely.
Right?
Okay. Thank you, Deepak.
Yeah, welcome. Okay, so yeah, that's it. Any other questions? Okay, all right. Well, thanks everybody for coming, and I'll see